Okay, this is another parametric integration question. The question this one does, it's more to do with the area that's being described, and a couple of little points about what are being described on the graph. So what I'm going to do is we'll first do the calculation, then find out where it's talking about, and then we'll discuss why there's a peculiarity in the answer it gives. Okay, so just getting to that point. There we go. So our first point is we want to do the integral. So the area is the integral of the function y, which is in terms of t. We want to do area as d times dx, but we haven't got x on its own, we've got x in terms of t, so we need to convert it to a form of t. So first of all, start with our dx dt, and that gives us minus sine of t. So when we put it into our area equation, we're now talking the integral from 0 to pi over 2, of 1/2 sine 2t multiplied by minus sine of t with respect to x. Got my trig identities over here that I need for all these trig functions. Sine 2t is this one, and when we change sine t into something we might be able to integrate, we multiply them by 2. So this becomes an integral from 0 to pi over 2 of 1/2 times 2 is 1, sine of t times cos of t times the sine of t again, so that's where we get a squared, and we get a minus in front. Look at the situation, it looks like to me like a f dash f to the n type function, doing an integral of an f dash f to the n, where the f is sine, or u equals sine of t, the u dt is cos of t, so we can rearrange that to say du t. Now you can actually turn it around so that dt is equal, dt cos t is equal to u, so we want to integrate with respect to u, so we can rearrange it so that we get cos t dt equals du, and you can do that substitution directly there, or if you want to go dt and replace it, du over cos t, and the du replaces the dt, and the two cos's cancel again. So we now wind up with an integral, which is the integral from 0 to pi over 2, and I'm putting these in quotes because we're no longer dealing with pi over 2. I'll discuss what happens to them in a minute. Of u squared, the du and the cos's, they cancel the t, cos t, so this is just with respect to du. Now the reason I put these in quotes is when we do the change, and Anna's pointed out that there's a couple of questions where they've done this. So if we take our limits, we've got a low limit and we've got a high limit, and they should be converted from x or from t, should change them into u. So if my limit is pi over 2, put it into my function, sine of t is 0, the sine of t is 1, and 0 is 0. So this actually should become an integral from 0 to 1, if you want to do it purely in terms of u. I'll show you that bit in a moment. So we've now got minus 1, put it back into blue. So we've now got minus 1/3 u cubed evaluated from our pi over 2 to 0, which actually should also be 1 to 0. we replace that now into the t form, minus 1 over 3 sine cubed t evaluated from pi over 2 to 0. That will give me minus 1 over 3 sine cubed of pi over 2. Well, sine of pi over 2 is 1. That's 1 cubed. Subtract 0 cubed, or sine of 0 cubed, which is 0 cubed. I'll just put no. In fact, we'll come back and put these in a moment. You'll see them. Actually, I'll leave them there and then I'll erase them at the end. So the result of this, sine of that is 1 cubed. We actually have minus 1/3. Okay. So the area it's talking about is minus 1/3. The u part that we were just talking about, if we deal with it in the top part, we actually get the same result without having to go back to sine. We have 1 cubed minus 0 cubed. This part down here, the actual evaluation of the sines. So we now get minus 1 over 3. So that's the actual area they're talking about. And if I show you on graph, here's their function. We're starting with pi as 0, and if I increase it to the point where pi over 2, we're talking about the area in that region between those two. Okay, so I'm just going to copy that graph down for a little bit of a further discussion. Okay, so we've got our graph. The area it's actually calculating is this area here. Now, that area, we traditionally would say that this area is in the positive region, so it's a third. What you need to remember is the direction in which we were calculating this area. When we put in the angle is 0, move it over a little bit. When the angle is actually 0, which is where we started, we're on the extreme right. And as we move towards the area that we're going for, to here, we've actually calculated this area the wrong way round. So because we've calculated this the wrong way round, our algebra and calculus has taken account of the direction. And it's turned around and said, well, you've actually done an area that's moving backwards. It's the actual direction, if you were to go from your x point to your y direction at this first point, going into the table. And that means you've got a negative area. So if you go from your x to your y here, it's a positive direction. So we're now going for in the area. So that would be coming out. So if we went from here to that way, we would get a positive area. It's called the normal to the area or to the plane. And that normal is going away from us, so it leads to a sign change. Because we're effectively going from the large value to the small value when we're integrating our x. That's why that all flipped around. Okay? That's the end of the calculus hasn't done it.